I talked about this at the ISSW and a couple of weeks ago at First Science too. And it's basically a simple test you can do to measure all these important fractional mechanical stuff that Carl talked about. And it's really actually simple, so everyone can do it. And everyone should do it. So please do it. So this is just a quick overview. I'll try to keep it short too, because we're already running out of time. But talk about traditional snow cover measurements that everyone's always doing. Then I'll introduce my super fantastic talk, and then super fantastic test, and then talk about what you guys can do and have a few conclusions. So traditional field measurements is what everyone's doing, is digging snow pits and doing stability tests. And these measurements have been around for a long time, a very long time. And they're kind of subjective, they're not very accurate, but they do give very good information. I mean, you get your layering, with stability tests you sort of get an idea of how strong the layers are. But it's tough to get accurate measurements which relate to snow stability, and that's really what we're interested in. And the traditional approach to this is you do a whole bunch of these tests on avalanche slopes that you tried to trigger but you didn't, and on avalanche slopes that did come down, and then you just do statistical comparisons, and this way you're trying to get to the important parameters of your system, what relates to snow stability. But the problem is, for instance, here a Rutschbach test, you have a person jumping on your Rutschbach test. How does that really relate to mechanical properties of the snow? And as our knowledge on avalanches is increasing, and Carl has talked about this, this is based on field observations and measurements and theoretical models. We know what we should measure, but you can't really measure it with these measurements. So what you need to do is this fantastic test, the propagation saw test. I think most people are familiar with the test, and it's basically you're doing a normal PSC, but you're filming it and you're putting these little dots in there so you can actually quantify what's going on in your test. And I'll show a bunch of videos. So how does it work? You need snow cover. You need a weak layer in there, or a weakness. It doesn't have to be a surface hoar layer, but it could also be a storm snow layer or something like that. You need some kind of markers, and I've been using different things, but yeah, they just need to be black and round. It doesn't really matter what you use. I've used roofing nails, which I painted black, and I've used plastic caps and stuff like that. Then you need your snow saw to initiate the fracture, to initiate the crack, sorry. I'm going to try and keep to your lingo. And then you need a digital camera to make a video of your experiment. And pretty much everyone has a digital camera in his backpack nowadays. And that's good enough. Here's a little diagram of the whole setup, and then these are some better markers I use. It's just a plastic cap, and I put a little metal rod in there so that you can put them in the snow like needles. And yeah, I'm not going to go into detail. If you're interested in doing the test, just ask me, and I'll provide you with the details. Here's an example of this test. Yeah. So you start sawing the weak layer, that little line there is the weak layer. Then if you reach that critical size, it propagates, and then if the slope is steep enough, it will slide down. So there's 3 different stages you're looking at. That initial crack you're making with the snow saw until you reach that critical size. Then it propagates rapidly through the beam. It doesn't always do that, obviously. You don't really see that here because it's too fast. And then if your slope is steep enough, it might slide down, as it does here.
Sorry, just a very quick question. The PST I've seen often being done from the bottom.
Yeah, you should do that.
From the top in direction of the motion of shear. Does that matter?
It matters for calculating the stuff. From a theoretical point of view, it does matter, but I didn't have a nice movie with everything in it. But yeah, you should start sawing from the bottom up.
Don't you get the same crack size either way, right? There's no difference
Yeah,
in the result. Is that,
I don't think that's right. There are no differences.
that's what I've read anyway, that didn't make any difference at any one
I
time
would
or
think
bottom
so,
as
yeah.
far as the crack size.
Yeah.
Okay.
I just know, I don't even know, it's just you're telling me.
Well, since they're asking that, that looks a lot longer than 100 centimeters, so we're using another
Oh,
standard
yeah,
length.
well, ideally it should be way longer than 100 centimeters. But a meter, people have been using a meter or a meter and a half just because you don't want to be digging for hours. But because you're cutting this, slab, you're introducing these free boundaries, and this really has a big effect on what's happening on the dynamics of what's happening within the slab. So if you want to get rid of that, you should have a really long beam, but it's just not practical. But the shorter you do it, like if you're doing these propagation saw tests on a day where it doesn't really propagate all that well, if you do short beams, it's going to propagate through your beam all the time. If you do longer beams, it's not going to propagate. So that's your edge effects there. Makes it easier to propagate. So here's the things you can measure with the test. So obviously the critical crack length, you don't need that whole video stuff for that. It's just how far did I saw until it actually propagated. And now this critical crack length, it doesn't matter if the fracture goes through the entire beam or not, even if it just propagates a bit and then you have and then it stops, it's still a critical crack length. It's independent on whether or not it propagates. Then the elastic modulus, I'll talk about all these in a little bit more detail. The fracture energy, the amount of collapse if it does propagate, and then if your slope is steep enough, you can also measure the coefficient of friction. So critical crack length it's quite obvious. It's how far did I saw. It's typically around 20 to 40 centimeters. Now Carl talked about, he doubled this number in his talk because you're doing this from a free edge of the beam. If you would do it in the middle of a long beam, it's typically about twice the size. Now, how does this relate to avalanches? I don't really know because you have only a 30 centimeter wide beam and it's just specific for this geometry, but it gives you an idea of what kind of size it is. It's not a few centimeters and it's not tens of meters, it's within the meter range. Carl has shown that there seems to be hardly any dependence on slope angle, if anything a little bit of an increase, and Dan talked about this too. I tried this by removing load and adding load to my beam, and it's just a fractal mechanical test. So with less load, which is over here, you need a longer crack. Then as you increase the load, the crack size decreases. So that all makes sense. Now the elastic modulus of the slab, and people might not exactly know what an elastic modulus is. Basically, it's a material property which will tell you how much your material will deform under a given load. So if you have a very high elastic modulus, it won't deform as much as if your elastic modulus is way lower. And you can measure this from by looking at the displacement during this initial saw cut, before it actually propagates. And now here you hardly see anything, but there is actually a little bit of displacement. You just don't really see it, does it? Now by comparing that displacement you measure with the displacement of an elastic material, you can match both up and then you can get a corresponding elastic modulus. Here, for instance, the red little lines are what we measured, and the black lines is of the best fit for an elastic material, and this was for a crack size of 30 centimeters. So that allows you to calculate the elastic properties of your slab. Now, you can also calculate weak layer fracture energy, and what that is it tells you how much energy you need to expand your crack by a certain amount. And to do that, you just look at changes in the mechanical energy during this initial saw cut. So here I've plotted for 3 different crack lengths the displacement of all these markers. And as you see, here's the crack length. As it increases, you get more displacement, more bending of the slab. And now for each of these markers, you can calculate how much it's displaced, and then you know the mass of your slab, so you can get your energy out of that. And so you can get an energy dependent on crack length as you increase the crack size. And which looks something like this, which theoretically should be a fourth order polynomial, which is that dotted line. Really matches up quite nicely, I think. And now the fracture energy is actually the slope of that curve at the critical crack size. And I've done this for a few experiments. This is preliminary results, it's not very good yet. And it's typically on the order of 0.5 to 1 joules per meter squared. Wrong unit there. Yeah, it probably doesn't mean anything to you guys. It doesn't really mean too much to me. Then if the thing propagates, you can look at how much collapse do you have, because that's really important for how much energy you have available during the propagation phase. Here's another test. With a thick layer of surface ore, we measured in the lavos. Obviously, there's a whole bunch of collapse here, and you can see the propagated collapse over here. It's a nice example. It's not a typical weak layer you'd be working with. It was like 4 centimeter thick surface ore, but it's a good example. Here you have the amount of collapse of all these markers within one row. The black one would be the one closest to the stop, and the red one at the far end, and you can see as the fracture propagates, they collapse one at a time. And even though it's not a single value of collapse, it's not the same collapse everywhere, you can sort of get an average amount of collapse of that weak layer. And this is very easy to measure. I've done this for quite a few experiments, and it's typically on the order of a few millimeters. I think my average is here 0.4 millimeters. And that one movie I showed was over here 3 centimeters, so that's more of an unusual value. There's a few collapses here on the order of a centimeter. I think they're typically associated with depth ore layers. We all know they collapse quite well. And these lower values, I think, were for, there's at least one layer in there which is storm snow, and that was only like a millimeter of collapse. But still, a millimeter of collapse is fair enough. And then the last one is the coefficient of friction after the propagation. And again, that little movie where the thing slides down. Essentially, as that block is sliding down, you have friction pulling it back, and you have gravity pulling it down slow, and you just get this a certain speed of your markers. Here, you look at the speed of the markers. The red one is normal speed, so collapsing. A peak when the weak layer collapses, and then it sort of erodes away. And the blue one is the slow parallel speed of the marker. During the initial collapse, it's quite fast, means there's not a lot of friction. And then afterwards, is really a constant increase in speed, so which means a constant acceleration. And that slope of that allows you to calculate your coefficient of friction. And I've done that for a bunch of experiments too, and it ends up to be 0.56, and with that coefficient of friction you can get a friction angle which turns out to be exactly 30 degrees. And that's the slope angle typical for avalanches.
Yeah.
Yeah.
That outlier on the far, as your first 1.7, do you know what kind of snowpack setup that one was? The one that's getting furthest out?
No, I don't
Often.
remember, but
Just curious.
yeah. But this is mainly from Switzerland, so my guess would be facets on the crust.
But if it was a surface or
Oh no, there's no surface. There's a little bit of surface ore in there.
there were a couple, right? Those bigger
Yeah.
ones are in there. Those bigger collapses are in that data set.
Yeah, yeah. No, they wouldn't.
They're not okay.
But obviously the friction is not only going to depend on what kind of reclayer, also the bed surface. If you have like an irregular bed surface, it might have a high friction. Okay, so with that awesome test, you can measure all these relevant parameters, and it's actually a quite simple field test. But you do need to measure density. People don't like to do that. I definitely don't like it, but you need to do it. What you see is that bending is really important. During that initial sawing, there's a tiny little bit of bending. It's small displacements on the order of a tenth of a millimeter, but you can measure that with a camera. It shouldn't be a big issue. I didn't show that, but you have that propagating wave, typical speeds in the order of 20 to 30 meters a second. And then Carl already talked about all this. Then after that reclayer is collapsed, you get friction, and the slope angle will determine whether or not an avalanche will happen. So what you guys can do is you can try this field test. I don't know if you ever do propagation saw tests or not, but I think it's an easy way. I pitched this at the ISSW. I only got 2 people doing tests for me right now, one in Alaska, one in California. But it's easy enough, and it will help get more data on more varied snow colors, more different kinds of reclayers, different kinds of slabs. I think it's important to get a handle on these properties. And I sort of scratched my head to tie this into this workshop, but I think there's a few things that relate back to the explosives work or the control work. I think that the critical crack length will tell you how big of an initial crack you're going to need before you get propagation. So it will tell you how big of an area of the reclayer you're going to need to break before it will start propagating. The fracture energy will tell you how much energy is required to actually break that entire area of reclayer. Then the elastic modulus of the slab will give you an idea of first of all, the coupling between your explosive and the snow, and also how well can I transfer that energy through my snow column. And then the amount of collapse is maybe a little less important for the blasting, but it will determine the amount of deformation through the slab during propagation and whether or not it can sustain that. So whether or not you can have fracture propagation. So in conclusion, it's a fairly simple test you can do, and you can measure all these mechanical properties of the snow column. There's no really special equipment needed except for these markers, which are not very heavy, and a digital camera, which is usually already in your backpack. And I think if people start gathering data, it can help to better understand and predict avalanches in the future. So if you're interested, I'll leave this up here. You can shoot me an email, and I'll give you more information about it. And that's about it.